Okay, in the last lecture we have been discussing about the vertical ascent of the rocket, and we calculated the burnout velocity in the vertical ascent, and then we were working out for the burnout altitude. Okay, so, in that context we wrote the equation y b equal to y 0 plus v 0 T b minus g 0 T b square divided by 2 plus z 0 I s p times T b ln m 0 minus T b ln m 0 plus m dot T b, and then plus the quantity. Okay, if you look into the last lecture, so this was the quantity that I am copying here in this place. So, this is the T b ln m 0 minus this quantity, and this is inside the curly bracket, this quantity, and here it is a minus sign. So, this minus and this minus, this becomes plus, and therefore, here we get a plus sign 0 to T b, okay, and this is m 0 plus m dot T minus m 0 divided by m 0 plus m dot T dt. Okay, and this quantity we were computing also last time. So, first of all, let us simplify this term. Okay, simplifying this term gives you, this is y 0 v 0 T b minus g 0 T b square divided by 2 plus g 0 I s p, and this becomes T b times ln m 0 by m b. This quantity is your m b. The quantity which is present here, this is nothing but m b. So, these two terms together we can write as m 0 by m b, and then this becomes plus, and if you remember last time we derived this term to be T b minus m 0 by m dot times ln and this quantity. Now, this minus sign can be absorbed inside this by taking m 0 from denominator to numerator, and numerator can be passed to the denominator. So, this will become then T b plus m 0 by m dot and ln. Now, this m 0 will go into the numerator, and this term which is nothing but equal to m b, this we can force to shift to denominator. So, this is the simple equation we have got for the burnout altitude in vertical ascent. Okay. So, irrespective of if you assume that the rocket is being launched from this place. So, rocket will in the vertical ascent, it will keep ascending vertically up, okay, while once it is leaving the surface of the earth, and if it is on the equator. So, you know that there will be a velocity toward the east. Okay. So, it will have a also horizontal towards the horizontal velocity toward the east. So, in the inertial reference frame, this will tend to this will appear as a velocity. So, rocket will appear to drift laterally also, but if we look from only for the vertical part. So, we will look that the rocket is ascending vertically, and whose equation is given by the expression we have derived here in this place. G 0 I s p times. Now, this quantity m dot which is present here, this can be written in terms of m and m 0. So, this m dot basically if you remember, we have written m as m dot t plus m 0. Okay. So, m dot can be written as m minus m 0 divided by t. So, this way what we are trying to do, that we are trying to eliminate this m dot and writing whole thing in terms of the burnout mass and the initial mass and the burnout time, rather than in terms of m dot. So, this becomes m 0 divided by m burnout minus m 0 times T ln m 0 divided by m b Now, once we have got in this format, some more simplification is possible by we can see that the term here ln m 0 by m b and here the term is ln m 0 by m b. So, we can take this common and add this term and let us look what the expression results in. So, we can take out the term ln m 0 by m b outside, and then the quantity inside the bracket will be T b plus m 0 T b divided by m b minus m 0 and plus T b. This simplification is little long, but not difficult. Okay, so, if we multiply this, we can see that m 0 T b term will cancel out, leaving us with the term m 0 times m b times T b divided by m b minus m 0 ln m 0 by m b plus T b. This is what we get in the next stage. Now, to do further simplification, we just put m 0 by m b equal to r, which is the mass ratio. Okay, so, this gives us y b equal to y 0 plus v 0 T b minus z 0 T b square by 2 plus z 0 I s p, and dividing this term m b in the numerator and the denominator, dividing by m b, we get here as the T b, and in the denominator 1 minus m 0 by m b. Okay, and similarly m 0 by m b plus T b. Okay. So, in this format now insert this value m 0 by m b equal to r v 0 T b minus z 0 T b square divided by 2 T b divided by 1 minus r, and this T b also we can take it outside and write it here in this place, because T b is present here, T b is present here. So, we can take it out of the bracket and write 1 by 1 minus r ln, and this becomes r plus 1. Okay, so this expression gives us the burnout altitude. Now, little bit more parametric representation of this equation is possible, and that puts it by the parametric representation we will be able to draw some graphs and have little more deeper look into the nature of these equations. Sorry. So, we define some design parameters such as thrust to weight ratio, and this quantity is greater than 1, dead weight fraction, S, and this we define as m s by m 0, and this quantity is less than 1, where m s is the structural mass at burnout. Then we define propellant fraction P as m p by m 0. M 0 is the initial mass. This includes the total thing, is the structural mass plus the propellants plus the payload. Mass ratio already we have defined. This we write as R equal to m 0 by m b, where m b is the burnout mass. This is the burnout mass. Then we define payload fraction as L, and this can be written as m L by m 0, and this quantity is also less than 1. Then payload ratio, so fractions are less than 1 and the ratio will be greater than 1. Okay, so payload ratio, this we write as G, and this we define as m 0 by m L. So, the inverse of this. Okay, so, we can write this as 1 by L. So, structural factor delta, this is m s by m s plus m p. So, this is the structural mass and this is the propellant mass and this is the structural mass. Okay, so, payload mass we have removed from this. And then we have a specific impulse ISP, this is T divided by minus m dot g 0. Okay, so, these are the design parameters of a rocket. Now, m 0 can be written as m payload plus m propellant plus m structure mass. Now, at the burnout, all the propellants will be burned. So, we can write this as m p plus m l plus m s, and this is nothing but mass of the rocket at the burnout m b, and this is the mass of the propellant. So, m b is nothing but m p plus m s. So, what we have written here m b is m s plus m propellant. And therefore, this we can also write as you can see from this place, this is your m z. So, m 0. So, m b can be written as m 0 minus m p. So, this implies m b by m 0, okay, m b by m 0 is nothing but 1 by r. So, if we divide on the right hand side, this becomes 1 minus m p by m 0, and this is the propellant fraction, and we have used the notation for propellant fraction as p. So, this is 1 minus p. Similarly, you can get the other relationship, delta is m s by m s plus m p. M payload plus m s plus m p minus m payload, and so this we can write as m s divided by m 0 minus this quantity is m 0. So, m l, divide the numerator denominator by m 0. So, this is m s divided by m 0, 1 minus m l divided by m 0, and this quantity we have written as the quantity S, which is the dead weight fraction m s by m 0. So, m s by m 0 is our dead weight fraction S, and this become 1 minus m l by m 0 is nothing but payload fraction m l by m 0. This is we have written as L. Okay. So, delta becomes equal to S by 1 minus L. Also, we can write m b by m 0 is equal to m s plus m payload divided by m 0, and this becomes m s by m 0 plus m l by m 0. Okay. So, this will be left hand side is 1 by r, and m s by m 0, this is the dead weight fraction S we have written as, and m l by m 0 as L. Okay. So, this is another relationship we are getting. So, this way you can combine the different parameters and write them, and these are very useful while reducing the rocket equation. Okay. So, if we remember from our the last lecture, so V b minus V 0, this was written as G 0 I s p ln m 0 by m b minus G 0 T b. Okay. And this we obtained by deleting the drag term and considering that the rocket is in vertical ascent. Okay. So, divide both side by G 0 I s p, and this gets reduced to ln m 0 by m b minus T b by I s p. G 0 cancels out. So, m 0 by m b we have written as r, and this we need to work out little bit. So, we can write m burn out is equal to m 0 plus m dot T b, okay, and therefore, T b becomes m b minus m 0 divided by m dot. Okay. So, this we can write as m b minus m 0 divided by m dot I s p. Now, if you remember that thrust by m dot 0 with here z 0 with negative sign, this has been written as ISP. So, this ISP we can eliminate from here. So, m dot ISP is there. So, this can be written as T by minus G 0, this is equal to m dot ISP. So, this gets reduced to ln r plus m b minus m 0, and this quantity we can write as T by Z 0. Now, divide the numerator denominator by m 0 in this term. So, this is m 0 by m b divided by m 0 minus 1 and divided by T divided by m 0. Let us write on a separate page. G 0 we can put here and T in this place. So, this is m b, not m 0. Okay, now, dividing this by m 0. So, ln r plus m b divided by m 0 minus 1, this becomes m 0 times G 0 divided by T. So, ln r plus m b by m 0, we know that this quantity is equal to 1 by r, this is minus 1, and T by m 0 G 0 we have written as the thrust ratio. So, in the beginning itself we wrote it thrust to weight ratio T by m 0 G 0. So, here we can write it as T by m 0 G 0. So, this is your T by m 0 G 0, and in the next step we can reduce this as ln r minus this quantity is nothing but r. Okay. So, this becomes minus 1 by r, and here we are changing the sign here because this quantity is less than 1 by r. So, we will put it in this way. So, what ultimately we see that V b minus V 0 by Z 0 I s p, this can be represented as ln r minus 1 by r 1 minus and 1 minus 1 by r, this we have also written as, if you look from this place, this equation m b by m 0, this is equal to 1 by r, and this has been written as 1 minus p. So, this implies that 1 minus 1 by r, this is equal to p, this is equal to p. Okay. So, this equation for V b minus V 0 by Z 0 I s p, this can be also written as ln times ln r minus 1 by r minus times p, 1 by r times p. Okay. Now, we can if we draw a plot for this by plotting r on x V b minus B 0 and divided by Z 0 I s p on the y x. So, this we take as y and this as the x, and this as the parameters. So, in this you look in this equation, basically we are trying to plot this equation. So, here minus 1 by r is appearing, okay, multiplied by 1 by r. So, basically we are trying to plot this equation, and this is a short representation of given here. So, if you do the plot, so your V v minus V 0 divided by G 0 I s p will be limited to this range. So, this shows that even if you increase the thrust infinitely, r becomes infinitely, it does not mean that the quantity V v minus V 0 by G 0 I s p will become infinite. Okay. So, your velocity remains finite. So, this is your operational range, basically operational range. We cannot go beyond this range, and we have to work within this limit, okay, where as already told that r is generally less than 10. So, this figure we will term as the velocity gain. Velocity gain means V v minus V 0 is your velocity gain. Velocity gain per unit thrust for unit propellant mass as a function of mass ratio. So, now one more figure we will draw. If we plot the burnout velocity on this x in feet per second, and m b by m 0, which is nothing but 1 by r on the x axis. So, you will get some this kind of plot, where on this axis let us say this quantity is 10,000, this is 20,000, this is 30,000, and here this is 40,000. Okay, this kind of curve can be plotted. Now, here if you look into this curve is for ISP for 350, this curve is for, so here ISP is equal to 350, this is for 300 and this is for 250. So, on the top we can see from this place that the velocity that the burnout velocity that you can achieve with the ISP of 350, this is limited. Okay. Similarly, for with ISP of 300, this is limited. So, while on the other hand, for injecting the satellite into the orbit, we require we require the velocity in the range of some 26,000 feet per second. Okay. So, this is not up to the 26,000 marks, but it is rather less. So, whatever the quantity we are getting, this is for the ideal case. Okay. So, we will do a derivation of how much velocity is required for the injection into the orbit. So, this figure we refer as burnout velocity as a function of mass ratio, a specific impulse and thrust to weight ratio, thrust to weight ratio, which is R. This is ISP, mass ratio we have written as capital R. And in this case the R has been chosen as R is equal to 2. So, using the equation that we developed earlier, this equation if put R equal to 2, okay, and G0 ISP you choose as 300, 250 and 350. So, you can do a MATLAB plot and you can assuming V0 to be equal to 0, because in the vertical ascent we are taking. So, in the vertical direction V0 is equal to 0. So, we can start with this and plot this VB. So, this kind of curve you will obtain. Now, for earthbound orbit, let us calculate the required velocity. We can write a very simple equation. This is the earth. Okay, so, here this is your radius of earth R e, and this we will write from here to here, this is the altitude. So, mb square by R e plus h, the necessary centripetal acceleration is provided by the gravitational force. This we cancel out, and here also this term will cancel out. Now, we know that on the surface of the earth m times g0, this is nothing but equal to m times m earth times g by r earth square. This is what we get on the surface of the earth. So, from here what this implies, this cancel out. So, m e times g, this is nothing but g0 times r e square. So, this we can, this term can be replaced by this term here. So, we will have v square by v square equal to g0 r e square divided by r e plus h. Okay, so, this is the velocity equation for the orbiting satellite. So, for the grazing orbit means the orbit of the satellite is same as the radius of the earth. Okay, so, this calculation 6374 kilometer is the radius of the earth. So, based on this calculation the following results can be obtained. So, we can write V equal to 25800 feet per second. This is for grazing orbit. Okay. If we go to 100 miles, 1000 miles up, so V 1000, this can be written as 23,200 feet per second. Okay. So, for injecting the satellite in the orbit, you require around 26,000 feet per second velocity for injection in orbit. And for lunar orbit, for lunar injection, for lunar mission, the required velocity is 35,000 feet per second. While the burnout velocity which is available to us, that will be confined to around 22,000 feet per second. So, the figure has been not very exact. Okay, so, here in this case this will be around 22,000 feet per second, that we get with the ISP of 350 say. So, we see that by using a single stage rocket, the required velocity, just we have done a simple calculation in the vertical ascent. So, required velocity is 26,000 feet per second, while we are getting around 22,000 feet per second. So, this is not solving our problem. And therefore, multi-staging of the rocket becomes in this case necessary. So, to sort out this problem, so we get by single stage rocket, (22,000 feet per second) velocity, while required velocity for orbit injection it is around 26,000 feet per second. Yeah. So, using a single stage rocket, therefore, it is not possible to inject the satellite into the orbit, and the kind of the specific impulse we have used here with r equal to 2. Therefore, a multi-staging concept it becomes a necessity, and multi-staging concept also it is efficient in the sense that say if you have a single rocket and you are taking it to the final orbit at the time of the burnout. So, you have to accelerate and accelerate a big mass from beginning to the end, and for accelerating a big mass from beginning to the end it requires a lot of energy, and that energy at the end will go as a waste, which are the structural masses. Okay. So, it is possible that the structural masses whatever we if we do the staging like the first stage, second stage, third stage. So, we can keep ejecting those masses the stages one by one as the burnout takes place, and therefore, this kind of design will be much efficient. Okay. So, what I imply here that this is the first stage of the rocket, this is the second stage, and then we have the third stage of the rocket. So, after the first stage propellants are burned out, so we can jettison it. Okay. So, if we jettison it, if we throw it out in the air, so we are left only with this mass, and only this mass needs to be carried out. So, this becomes energy wise or propellant wise more efficient. Okay. But the problem involved with this is jettisoning is this is little more complicated complicated mechanism, and 40% of the rocket failures in the past has occurred due to this stage separation. So, we have to separate out jettison this, we have to separate out this stage, and this is a this involves a complex mechanism, and in that course the basically the failure occurs. If you are not able to eject this, so whatever the previous design you have done this before the launching of the rocket, the whole design comes as a failure. Okay. You cannot go to the final orbit with so much of mass attached to the second stage. So, we will discuss about the staging of the rockets also. Okay, as we have done the parametric representation of the burnout altitude, burnout velocity, in the same way we can also represent the burnout altitude in parametric terms. Okay, and that gives us a more comfortable way of describing or presenting the equation and doing the parametric studies, representing the things in terms of the graphs. Sorry. This is the equation that we have written for the burnout altitude, where y b indicates the burnout altitude. Also, we have written T v by ISP. This can be written as T v by minus T by m dot z 0. ISP is nothing but this quantity. Now, m dot can be written as m b minus m 0 minus sign here divided by T burnout. So, this T b and this T b, this will cancel out, leaving us with Z 0 by T, and this we can write as m z minus m 0 minus m b, minus sign we have absorbed inside. Now, if we divide it by, if we take m 0 outside, so this is m 0 times G 0 1 minus m b by m 0 divided by T. T by m 0 z we have written as the thrust ratio. So, this can be written as, let us take to the next page. So, we have T b by I s p equal to 1 minus T by m 0 z 0, and m b by m 0 this is nothing but 1 by r, this quantity, and this we have written as a small r. So, ultimately this reduces to this expression T b by I s p. Now, we can utilize this expression in reducing the expression for the y b minus y 0. So, by putting v 0 equal to 0, that is initial vertical velocity is 0, so this becomes y b minus y 0 is equal to 1 by 2. We divide both the sides by G 0 I s p square. Okay, so, this will give us G 0 T v by I s p square plus G 0 by G 0, and I s p times T v we have, we can insert from here. So, this is I s p times T b divided by G 0, G 0 we have already taken here into account, this is I s p square times 1 by 1 minus r ln r plus 1. Okay, so, the quantity which is present here, this is nothing but I s p by T v by I s p, and T v by I s p just now we have derived here in this place. So, just we need to insert in this place. So, y b minus y 0 by z 0 1 by 2 times T v by I s p square. So, this is 1 by r square times this cancels out, and here we have again 1 by r times 1 minus 1 by r times 1 by 1 minus r ln r plus 1. So, this is the expression we have got now. this was our with a minus sign V b minus. See here we had this minus sign here in this place, minus G 0 T b square divided by 2. So, wrongly we have put here the plus sign. So, we make a minus sign here in this place. So, this is the burnout altitude and we utilize this here in this place. So, here we will have a this is fine, this is plus sign, here we will have a minus sign, we will have a minus sign here in this place. So, finally, what we have got y b minus y 0 divided by g 0 I s p square equal to 1 by r times minus 1 by 2 1 by 2 term is also present. So, this is 1 by 2 times r square times 1 minus 1 by r whole square. And for this also we can do a parametric representation in the same way as we have done earlier. Now, so all the parametric representation can be done, but what our objective is ultimately to study that with the various factor of the parameters how the rocket will be behaving. Okay. If we change some of the parameters, then what are the limits set. So, basically we would like to optimize the parameter in such a way that our burnout altitude becomes maximum. In the multi-staging rocket, again the altitude, the maximum altitude that can be reached, that can be optimized with respect to the parameters. Okay. Similarly, in the case of the single staging also, the maximum altitude that can be reached, that can be optimized with while doing the parametric study. So, the situation given at our hand, what are those parameters, what are our specific impulse given, the what kind of rocket we are using, what is the launch altitude. So, depending on that we will have some set of already prepared rockets. So, nowadays the ISRO as it is using, so it has already the PSLV or the GSLV, it is already there. So, those rockets will be used for launching. So, every time modifying and designing the rockets, it is not possible. So, use the already the built rocket and what is your mass. So, at what altitude you will be able to put it, and when you need to do the ejection. So, all those things you can plan in the beginning itself. Okay. So, the next step we will take it for the specific energy required or the specific energy at the burnout. So, how much it will be. So, in that case we will represent the burnout energy as the E b, and this can be written as 1 by 2 per unit mass. So, this can be written as 1 by 2 V b square plus G 0 times Y b. So, this is indicating the potential energy gain, and this is the burnout kinetic energy, and this is indicating the total energy per unit mass. So, at the time of burnout, how much this specific energy will be, that need to be calculated. So, you can see that if you need to put a satellite into certain orbit. So, obviously, at the time of burnout, some of the you need this quantity E b to be larger than the 1 by 2 V b terms, 1 by 2 V b square term, because this is the energy which is going along with the rocket. Okay, and this is the potential energy to be will be gained. So, if this quantity is equal to this, means simply the G 0 Y b becomes 0. So, this means simply the G 0 Y b becomes 0. So, that is we are not looking for exactly this kind of situation. What we are looking for, that y b is equal to here around 250 kilometers. Okay. So, that our problem of putting the satellite in the orbit is solved. So, we will do, instead of doing the plot for this, we will make a plot for E b, the specific energy, in the same way like E b divided by I ISP square times G 0. Okay. So, we will make a plot for this in the next lecture, and then see how the variation is take place, and you will see that we get exactly the same kind of curves for this also, while we plot this on the y x and r on this x, and this gives us the operating range. Okay. So, these are to be discussed in the next lecture. So, next lecture we will try to make it the last lecture, because we have already given 3 lectures on the rocket dynamics. So, in the next lecture we will do the specific energy study, and thereafter the multi-staging of the rocket. But in the multi-staging of the rocket, again what I was telling about, that we can do the optimization, but that process is complex and it requires more number of lectures, and obviously theoretically finding out the optimized value, it is difficult. So, we have to make many more compromises, means many more approximations, and by making the approximation we go away from the actual situation. So, that part we will omit, and we will just confine ourselves to the multi-staging of the rocket, and how much will be the altitude achieved or the velocity at the time of the burnout. So, thank you very much. We continue in the next lecture, and that will be the last lecture for this series, I hope. So, thank you.